Let's take a look at an approach for actually finding shortest paths in graphs, and we'll use this example once again. It'll help to actually have names for the other nodes, so I'm going to add those in. So let's remember what breadth first search does for this graph, starting from A. We mark A as visited, and we add it to the open list. We pull it off the open list and add all the neighbors of A to the open list, which are C, B, and D. Then we choose one of these nodes, say C, and add all its unexpanded neighbors to the graph, but all its neighbors are expanded. Do the same thing with B. B has F, and D's unexpanded neighbors are E. All right, now F's unexpanded neighbors are G, and E has no more unexpanded neighbors, so we've finished this depth first search. What we get here is that by the assumptions of a breadth first search, the shortest path from A to B is this direct link from A to B. The search would have actually terminated here, but we ran it out anyway. So these are supposedly the shortest paths in terms of number of hops to all these nodes. Does that actually make sense? One hop to C, one hop to B, one hop to D, 2 hops to F, sure. 2 hops to E, sure. 3 hops to G, 1, 2, 3, 1, 2, 3. Yep, there's no faster way to get to G. So this actually does the right thing in terms of number of hops. But let's take a look at what happened when we went to expand B. At this point, even though we have a shortest hop path to B, we don't have a shortest length path to B. All we know is that from A, you can reach C in 3 steps. Well, and that's really all we know. Even this A to D, we don't know. There might be a half weight path that goes from C to D. But we do know that there's going to be no faster way to get to C, right? Because that is the shortest edge out of A. Any of the longer edges, we're assuming we can't take negative weight edges that would cause this 4 to get smaller than the 3. So all we really know is that this 3 is the smallest. So what we should do is not expand B, but we should focus in on C. We now know that there's a path that actually can get us there in 13, right? This 10 edge plus the 3 that it takes to get to C. So we can get to B faster than 15. We can get to B in 13. Now, is that the shortest possible path for B? We don't know, because we know that we could get to D in 4, and maybe there's a length 1, ignoring the graph for a second, maybe there's a length 1 path that would get us to B, which would be even shorter. So all we know from what we've done so far is that the shortest path from A to D is 4. So let's lock that down and pull D off of the open list, and let's focus in on D. So D has edges to B, F, and E. Here's B, and here's F and E. So this path to F through D, going to add another 7 for a total of 11. And this path to E through D is going to add another 3 for a length of 7. And remember, there was also a D to B link, which would add 9 to this, which would get us there in 13. And we already knew how to get there in 13, so that doesn't really change anything. So based on this tree, we know the fastest way to A, C, and D. And of the ones that we have also been able to reach, we know that E has the shortest distance, which is 7. And there isn't going to be any faster way to get to E, because there aren't any other nodes that we could get to and then get to E faster than 7. So we can lock that one down, pull it off the open list, add all its edges to the non-completed node. So E can go to F, and that has a length of 5. So we could go 7 steps to E and then another 5 to F for a total of 12. No, we can already get there in 11. That's probably not a good idea. From E, we can also get to G in 1 step, which would have been 7 plus the additional step for a total of 8. And that's all we can reach from E. Looking things over, we now know that G, the fastest way to get to G, is 8 steps, because the only other ways we could get to G would be to visit one of the other nodes and then go to G, and that will have to be longer than 8. We can lock it down. And now we pull it off the open list and look at the edges out of G. So G can get to F in 2 steps. Oh, and that's an improvement, because before the best we could get to F was 11 steps. So now we can get to F in 10. Can we get anywhere else new? No, because the only nodes that aren't complete now are B and F, and they're already in the picture. And in fact, now we see that the fastest way to get to F is going to be in 10 steps, because the only other way to get to F that we haven't considered is getting there through B, and that's going to be longer. So we can lock this down. All right, let's look at F. What edges are coming out of F to uncompleted nodes? Just this 1 to B. That would have been F is 10 steps, plus 1 more would be 11 to get to B. That's an improvement over what we had before. And that's it for F. And now the only node that we've got left to think about is B. There is no way to get to B any faster than 11, because there's no other place that we can go and then get to B. So we can lock it down. And that finishes the picture. We now know what the shortest distance is from A to every other node in the graph. The distance to B is 11. Now we've kind of lost a little bit of the information of how we get to B in 11, but we'll deal with that in a little bit.